All right. The previous streaming session ended with us creating this new type of a network. And now we want to test the pandemic model on it. So we have this pandemic model, and we have this computational experiment, and we just replace rich club network here with Barabasi, and it should work. And it seems to be working. Okay, let's now good. So it seems to be working. But now the actual computational experiment that I'm about to run is described here above. It's point 3, social isolation experiment. So let's try the following. Let's try to run the pandemic on our network with those super connected nodes, but then let's take exactly the same network, but let's isolate one of the nodes. Let's pick the most connected node and isolate it from the rest of the network. And see, that's equivalent to like canceling one parade or one concert on a stadium. And let's see whether it actually changes the dynamics of disease propagation in this network. So we'll need to write this thing that deletes, that isolates the most connected node. So let's do that. Let's do our, okay, you know what? A rich club network, can I just delete it by now? Do I still need it? Okay, let's keep it for now. Why would I delete it? So let's go here. So Barabasi network, I created a network of 100 nodes, and then let me mess with it. Oops, I pressed A. I wanted to press B. I want to be below this cell. So let's catch them, isolate the most connected node method. So let's first just fool around. So we have our network G, which is created, and it's an object, but we can print it. We don't, I mean, it's horrible because it's 100 elements, but we can plot it, right? It's the same thing that's shown here. Good. It has this super connected node here. So G degrees. Oh no, we don't have G degrees. We have degrees G. Degrees G is like, yep, this thing. So we have a node with 32 freaking connections. Wait, what? What is this array? Oh, these are frequencies. These are frequencies. Yeah, okay, so we have a node with 32 connections. It's obviously this node in the very middle. So here's what we want to do. We want to find it. And then we want to set all of its connections to nothing. And we want to go through all nodes it used to be connected to and remove it from the list of connections, right? So for every edge, we should essentially delete edges. Oh, basically, that's a good point. Maybe we should add it as a method to our basic class. Let's do that. So we will want to delete edges. We can also write a method that deletes a node, but I don't want to do that because I'm afraid. And the reason I'm afraid is that it's kind of related to my last tangent at the end of the previous video. Even though, so there is a little bit of a kind of split mind situation now to all of this code, because some parts of it read as if nodes can be anything, as if node keys can be anything, like strings or numbers that are not necessarily in a sequence. But at the same time, all the creation functions now just create nodes with keys that are a sequence of numbers. And I'm just afraid that there may be pieces of code that kind of assume that all numbers are taken, and that if we delete a node and we'll have like node IDs like 0, 1, then 2 is missing, then 3, 4, and so on, something will break. So it's all fixable, but I just don't want to engage with it right now. So because of that, I won't be deleting this node. I will be isolating this node. There is no difference between the two for the purpose of pandemic propagation, because if the node is not connected to anything else, then it cannot be infected. But it will just make everything safer. Okay, so let's actually amend. Let's go to this plan. Oh Lord, let's go to this plan that I sketched, and let's write the parts that we need to do. So write delete edge method, learn to find the most connected node, delete all edges from this node to all other nodes, make it a neat function that is easy to use, right? So this is like the plan. Let's start with the first point, write delete edge method. Okay, so we have get edges, we have add edge, we want to add delete edge here. So let's change the test first. Add edge 01, add edge 02. Okay, so now we create a graph of 3 nodes. And now I want to delete del edge from 0 to 2. And it won't run because I haven't implemented it. Yeah, but we have a test case. So let's implement it now. Define del edge. I don't like this del, delete edge. Let's call it delete edge. Let's use human language. Okay, delete edge, and it gets self, and it gets node 1, and gets node 2. All right. So there are 2 options. Either this edge actually exists, or maybe it doesn't. So let's first handle the case if it doesn't exist, if we called it by mistake. Let's keep it safe. So if node 1 not in, because the way we keep the graph is in this gdict dictionary, right? Remember, gdict of a node is a list of all nodes this node is connected to. So if node 1 is actually not in self gdict node 2, so if they're not connected, just whatever, be done with it. We can all, if you want, we can return false, like we failed. This edge doesn't exist. Why? Okay, let's just return false. It's like you can return false if you want to check whether the operation was a success. Like screw it for now, because we don't use it anywhere else, so it's kind of silly to have it here, not in other places. So just return. This edge doesn't exist. Done. So now, if we reach this point, it means that the edge does exist, and we go and we just remove the cross references. So we do self gdict node 1. We need to remove, so this is a list now. This is a list that includes node 2. We should remove node 2. And I think we can just do remove node 2. I think that's how lists work. We have a method called remove. And then self gdict node 2, remove node 1. And that's all right. Yeah, we don't delete these nodes, we just remove the edge. We don't have to finish it with return. It will auto return. We are not returning any value anyways. So now this should work. Yep, it works. So see, we added edge 0, 1, we added edge 0, 2, and each of this operation also added a corresponding node because that's how we coded it. But then we removed edge 0, 2, and the node is still there, but it's no longer connected. Yay! We now can remove edges. Now we go back to our little playground for isolation. So now, point number next. Let's find the most connected node. For like what? How do we do that? All right, here's how we do that. So we can do something like that. We can, I'm debating whether to do it like fancy way or slower way. Let's do it slowly. So remember, so we have okay, degrees. Actually, you know what? Let's look how we created this thing, how we created this histogram, because we have this function somewhere, right? Where is it? Degrees here. So we have this lovely pair of lines here that where we iterate through this dictionary for node links in G dictionary items. This is how you iterate through a dictionary in Python. And then something. So let's steal this line. We'll need this line. We're going back. So for node links in gdict items, okay, print node links. Oh, yeah, let's generate a different one. Let's actually generate a small network. Small network, yep. Okay, let's generate another small network. I want one winner. Okay, so node number 1 has 6 connections. It's like here it's on the histogram. Here this node is in real life, right? So gplot, yep. So this node. plt subplot 1 to 1 gplot. Okay, and then after deletion I will plot it again, and hopefully we'll see how this node won't be connected anymore. So we iterated through the list, through the dictionary, and we got node, and for each node we got the number of links, right? So let's write a function that deletes one node. The most connected node, which means that we only need to find like the most connected node. Sure, let's do that. So like most, like highest so far equals 0, best node equals none. But then if length of links, this is the degree, is above highest so far. So if we encourage a node that has more connections than the previous best node we've seen, let's update our understanding of what high means. High so far is length of links for this node. And best node is now this node. So this node is our current champion. Print best node links. No, links won't work. So print best node gdict best node. So we expect for this particular graph, we expect to find node number 1 with connections 0, 2, 3, 4, 5, 6. Yep, that's what we found. Good, so we found the best node. So let's isolate it. 4. So what do? We'll go through all nodes to which this one is connected, and we'll remove the edge. So for node in, all nodes to which node this is connected, this one is connected, G delete edge, going from the best node to the node. Yay! 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 We've done it. It's kind of hard to, yeah, so because the graph had changed, it's not quite obvious. So this node, it's not quite obvious like which node survived and which node didn't. I think so. I'm pretty sure that, yeah, there is a way to keep the layout from this graph and to just plot the new graph using the layout from the previous graph, but I don't remember how to do it. And I don't want to engage with it, but you can probably convince yourself that this graph is this node, is this graph, sans with one node disconnected. Actually, where is it? This node, the disconnected node, why isn't it shown? Uh-oh, why isn't it shown? Isn't it supposed to be somewhere? Even if it's not connected, it should still be on the, okay. Let me recalculate. I don't like that. I don't like the fact that I don't see a lonely node here. Uh-oh. Why? All right, let me go to my plot function, because remember there was some other way of plotting stuff. So right now it's used Kamada Kawaii layout. Let's use Spring layout. With Spring layout, disconnected nodes will be really, really obvious. So again, running this thing, then running this thing. No, there is no disconnected node. How come? Did I delete it somehow? Print G. Now there is a disconnected node. So we have a graph of 10 nodes. That's true. Something is wrong. All right. So let me add G equals Barabasi 10. Okay, let's go with a simpler plot of 3. 3 is fine. So we created a triangle. Aha. So this node didn't get disconnected completely. I have a mistake somewhere. Like it killed one edge, but not the other edge. Mm. What do we do? All right. So the cool thing about the Barabasi, about this Barabasi 3 is that we'll always have a triangle. So if I rerun it, it's totally predictable. It's always the same result, which means I always have a bug, but it's the same bug every time. So we can use it for troubleshooting. Another way to troubleshoot it would be to set, like, to change our random numbers generator so that it always generates the same random number. To check the seed. I don't actually remember whether we did it. I think we did at some point. But yeah, all right, whatever. We can troubleshoot this thing. So, as we are killing the node here, let's print it. Print node. Yeah, why not? We have a mistake, which I don't understand. So look, when we found the best node, in this case, well, there are three best nodes. It doesn't matter which one we pick, because there are three nodes, all with two connections. So it picks some node with two connections. Good. Then it prints the best node and the list of nodes it's connected to. 0, 1, 2. Good. So node 0 is connected to node 1 and is connected to node 2. All as expected. Then we have a then we have a loop for node in gdict best node. So we expect that node will go through this dictionary, which we know to be, to this list that we picked from dictionary, and we know that the list is 1 and 2. So we expect the node to be equal to 1 and then to be equal to 2. And we print it at every step. But somehow that's not what happens. We only print 1, so we never print 2. And I think what's happening is that as we delete edges, we're actually changing this thing as we go. I think, I'm not quite sure. Okay, let's add copy here. Yep. Okay. Okay, let me explain what happens. So what happens here is, like, that's bad coding. This is bad code. This is bad practice, real smelly. Like, no, don't do that. What happens is that we have a for loop, and node is supposed to take values from a certain list that sits in a dictionary, but it's a list that we pick from a dictionary. However, inside the loop, we are messing with this dictionary. We are deleting elements from this list. And it just creates a really unfortunate, like, kind of logic where this line sounds as if you know what you're doing in advance. Like, okay, here's a list for you. Please take different values from it. But then you mess with the list as you go. And different languages, I think, if I remember correctly, like, do different things in this situation. And you can use it for all sorts of hacks, potentially, but it's bad. It's bad. Let's not do that. Because we're making it's like hard to predict how this code will behave. So we don't want this to happen. a good way to do that. So how to make it work? We want this list inside the for loop to not change as we go through the loop. And if you add copy to the end of it, it achieves this goal. Because what will happen, we'll look at the dictionary, we'll take out the list, then we'll make a copy of it. And then even if we mess with the dictionary, the copy of it won't change. I'm not sure it's good code though. I mean, how do people actually use that? Actually do that? What's the appropriate way of doing that? We had something like that the last week. Remember when we worked with the list of points to be infected? And then the first time I coded, I kind of changed the list of, changed which points are infected as I was going through the list of points that are infected, which created this strange explosion of infection. And then I changed it in a way that I kept a list of points that will be infected at the next step, but I didn't let it mix with the points that are infected at this step. And then there was, and then like I switched to the next day. And here we have kind of the opposite of that, because we're not adding, we're deleting, but it's pretty close in spirit. As we delete, we still want to go through every point from the original list. Yeah, I guess that's fine. I guess that's okay. It looks a little bit awkward, but that's okay. So through, yeah, we go through the list of all nodes. So now it should work. Now it works. I can remove this print. I can yeah, but it works. Let's go slightly back. So let's first change back to Kawaii visualization, just because it's nicer. Now let's go back here. Yep. So the original, this thing. Let's now make it. Oh God, how did it do that? No. Now let's create a slightly larger network. Instead of 3 elements, let's try 4 elements. Oh, that's fun. So really, yeah, so this is the most connected node. It has 3 connections. If we delete it, then the remaining nodes just form a line. Nice. So it works. It works. It works. Yep. How's about like network of 50 elements? It's hard to see now, right? So let's, instead of looking, let's do 100 elements, but instead of looking at the plots, we will look at degrees of this. So degrees before and degrees after. Yep. Okay, so look. Yay. So originally, the largest node had a degree of 22. And the next largest node had a degree of 19. Now, after the trimming, the most large node has a degree of 16, 17, 18. 18. Yep. So it's actually the same node that used to have a degree of 19, but why does it have a degree of 18 now? You know what happened? It used to be connected to the most connected node, and now it's no longer connected. But still it's the same node. So it seems that it worked, right? So the highest connected node disappeared. The shape changed slightly because all connections from this node also disappeared. Like there was this little peak for 6 nodes, so 6 was slightly larger. Slightly more nodes had 6 degree of 6 than degree of 5, and now slightly fewer nodes have degree of 6 than degrees of 5. But basically, yeah, that was all the influence of this one node that we deleted. So it seems that it's working. It's working, and now we need to turn it from the sketch into a function. So let's turn it into a function. We don't want that, we don't want this, we don't want any visual. Well, maybe we keep it as a test. So let's keep it as a test. The actual deleting part is this part. Hey, okay, so define remove the hub G, and then we paste all of that. So let's trace that, like read it and think aloud. Remove the hub, we get the yeah. Let's add a docker string, isolate the most connected node. That's good. Let's remove this thing. Height so far equals 0, best node equals none. Yeah, so G is an argument, but everything is fine. Do we need to return anything? No, we don't. Print, we comment because we don't want printing for node. Yep. And this is a test. And the test is now that after we calculated these degrees, and let's suppress output. So in this point we call our function remove hub. Let's dispense with the remove hub G. Does it work? Yeah, it works. It's not that spectacular. In this case, there was a node 16, 17, 18, 19. There was a node with 19 and now it's disappeared and we only have a node with 16, but it still works, right? Here there was a node with 23, now we don't have a node with 23. Yep, good. So now we are ready for using this newly written function for a little experiment. Remove hub. So our computational experiment, that was a computational experiment. Does it still run? Yeah, it still runs. This is a computational experiment with a network, Barabasi network of, let's say, 100 nodes, and let's run it for 50 trials for 30 steps. Yep. Now let's do the following. Let's run it. Let's plot it. Oh no, we cannot do that. So ideally we want matching networks. So every time we have a network, we want to run an experiment on it. Then we remove a hub from this very network. And then we run an experiment again. All right, let's do that. So we do a network, we make a network, we run an experiment, then we remove hub from this network, and then essentially we run an experiment again, except that right now it will overwrite the first experiment. So how to make it work better? Let's do the following. Let's make our history not n trials wide, but n trials by 2 wide. So instead of n trials, we'll keep n trials and then n trials again. And in every case, like the first n trials will be for the original network, and then like a matching element in the second half will be the same network minus this hub. Does this make sense? So like the first network, untrimmed, will be at element 0. Same network with hub removed. The results of running our model on it will be in element number n trials. Then number 1 is another experiment, n trials plus 1 is another experiment, and so on. So to make that happen, we will add plus n trials here. And if we run it, it will already work. But the plot is now incorrect because it now combines all of that. So we now want 2 plots here. And for the first plot, so we'll have a first plot and the second plot. And the first plot should only, so let's just change which part of this history thing we're averaging. So for the first plot, we are averaging all, so we take all time points, but not all trials. We only take trials up to n trials minus 1. And colon n trials will do that. And for the second mean, we'll do like everything from n trials and until the end. So that's how you code it, right? Colon n trials means everything from 0 to n trials number 1 included. And n trials colon means from n trials included to the last element. Nothing else changes. Let's label them. I think that we can do it like that. Label equals like original Barabasi. And for the second one, we do label equals trimmed. And we do POT, legend, location. If I remember, I think it's loc, right? It's like upper right. Okay, let's try that. Yay. Oh, look at that. So, you know what? Let's make it slower. It seems like it's working, right? We have two different curves. Let's make 100 trials. And let's make it slower. And we'll make it slower by reducing the probability. Let's actually like make that into a constant prob for the probability of propagation. And we'll set it to 0.1. Like propagation probability. Propagation probability. Okay, 0.1 is too slow. 0.2. Yay! Okay, so what happened? It's actually pretty nice. Look at that. We have two curves. You know what? Let me run it with like ridiculously high number of trials, like 500. And it may be a little bit slowish, but I just want to describe curves that I see them being smooth. Look at that. You know what happened? We flattened the curve. So by just canceling one event, we already had a result. See? We removed this most connected node. And on average, it means that it took longer for the disease to spread in the network. Without one node, with one node disconnected, the maximum is lower, but also it lasted for longer, right? Because it didn't change the total number of cases. Well, it did change the total number of cases because this technically this node is now disconnected. So this node, because like the way we implemented it, this node didn't fall sick, but like the total number of cases is lower by 1 out of 100. But the dynamics is actually pretty different. The maximum is lower, and the tail is wider. It lasted for longer. Okay? All right. So originally I promised that, so yeah, here we draw a line here. We enjoy that. We rejoice in this result. And in my original plan that I wrote there, I said that I will also show you how to excise this class into a Python module. But I'm out of steam now, so let's park it till the next session. Your homework now is basically to reach this point. So try to. I will post that on GitHub, obviously, but try not to look at my code on GitHub if possible, and try to follow this coding process and maybe watch the video first, because I made some questionable choices in the process and some of them I corrected. So maybe ideally watch it and then try to implement parts of it by memory. And if you cannot, then return to the video, and only if this doesn't work, go to the code on GitHub. I think that would be most productive. And your goal is basically to achieve something like that, like what we have on the screen now. But make sure you test your methods and your functions in the same way as I did it, kind of like in spirit of that. So make sure you test each of them and each of them actually works, and you can actually delete edges and you can actually disconnect the most connected node. So don't just try to get two curves that are superficially similar to these two, but make sure all of your steps work. But when your steps work, you should be able to reach this result and see these two curves. Okay, great then. Till later. Good luck.